All right, well, Leslie's asked me to talk a little bit at the Science Byte about tsunamis, so I will do that. As some of you may know, I studied under Chris about 40 or so years ago. I learned lots of things from Chris, including putting too many slides in a presentation. So you're going to have to listen really fast. But I'll talk about tsunamis with a primary focus on a special type of tsunami, and that is tsunamis that are produced by underwater landslides. But I'll have some general comments about tsunamis as well. Just, by the way, the title slide here is part of a model that was done for the January 26, 1700 tsunami created by a giant earthquake, a great earthquake off our coastline somewhere. It was recorded in Japan, and that's how we know precisely when it occurred. And it did a lot of local damage along the coastline. There are First Nations stories and certainly evidence of that damage. So just to make sure we're all on the same page, a tsunami, as you probably know, is a series of waves created when a body of water, ocean, it can happen in lakes and reservoirs and fjords and so forth as well, is rapidly displaced on a massive scale. And I'll come back to the ways in which we can massively displace a body of water in a minute. It's obviously a Japanese word and means simply harbor wave. So tidal wave is not a correct term to use, as I'm sure we've all learned since 2004. Okay, most people divide tsunamis into four principal types, those created by faults, and I don't have a schematic for that, but and these faults, the movement on these faults, are generally associated with magnitude 7.5 earthquakes. In fact, the Hawaii and Alaskan Tsunami Warning Center, the folks there don't even get out of bed unless the earthquake is greater than 7.5 to start worrying about whether there's going to be a tsunami. So remember that number. It'll come back. So basically what happens in this case is, and I have to use my hands here, we have a flat seafloor, say, or a seafloor, and all of a sudden we have a fault rupture, and part of that seafloor moves up suddenly. It can move up by typically a few meters over a very small period of time, very short period of time. So that sudden impulse, and then it's over with, and that will move the entire column of water above that fault rupture, which creates the wave that is the tsunami. The second class, and there are two different parts to it, are landslide-generated tsunamis, and that's what I'm going to focus on today. And there are two types. Subaqueous, in other words, the landslide is entirely underwater. Or in coastal areas, we can have subaerial landslides, and this is where a side of a mountain falls into a fjord. And I'll show you some examples at the end, unless I run out of time. And then a couple of other classes that are not so common, volcanic eruptions, and the best known of these, there have been several, but the best known is Santorini, also known as Thera, in Greece, which erupted, and stories of Atlantis and so forth circulate about that, and it's been tied to the Minoan civilization. Its demise is probably not true, and so forth. So, and then asteroid meteorite impacts, the best known of these, happened 65 million years ago at the Cretaceous-Tertiary boundary, which had dramatic consequences for life on Earth. But I'm going to focus on the landslide-generated ones. But firstly, again, a little bit more. They're not like wind waves, and I'll have a little diagram of that in a minute, that only act on the upper part of the water column. A tsunami involves the entire water column from the seafloor to the surface. The speed of propagation is root gh, right? Square root gh. So where g is the acceleration due to gravity and h is the water depth. So if you're in 4,000 meters of water depth, which is deep ocean, that tsunami is traveling 713 kilometers an hour. And it will have a wavelength from crest to crest of that wave of 213 kilometers. Now, if we put it in the context of what we would find around here, for example, if we had a tsunami created on the Cascadia continental margin in, say, about 1,500 meters water depth, which is not unrealistic, the speed of that wave would be about 437 kilometers an hour, or it would arrive in Tofino in about 10 minutes. So it's not an awful lot of warning to go running up a hill to get out of the way. So the difference is when you have wind waves, out at sea, of course, there's wind stress on the sea surface creating the waves. Those waves then approach land, and eventually they feel bottom to such an extent that they break. A tsunami is barely detectable at sea. It can be a few centimeters at most at the surface, and by the time it gets, but it involves the entire water column. So when that reaches shallow water, of course, that wave now is feeling that bottom more and more and more, and that is essentially compressed, if you like, that motion, so the tsunami rises and slows down, and eventually spills like a wall of water. And I think the next one shows. Well, that's commonly used. This symbol from Japanese is commonly used as a equivalent for a tsunami. Well, in fact, it's not. That's not what a tsunami looks like. This is what a tsunami looks like. So the water basically will rise and rise and rise, and then will spill over the coastline as a spilling wave that will just seem to keep on coming. That's certainly the history in the Indian Ocean one in tsunami in 2004. So let's focus a little bit on underwater landslides. I talked a little bit about how faults can create tsunamis. Here in this little schematic, we have to pretend that what's marked here as row 2, this gray mass here, is some land under the ocean which is going to fail. It's going to slide down the slope. Well, the first thing that's going to happen is, right here, we're going to pull the water surface down. We're going to create a hole in the ocean here. As this moves this direction, it's going to tend to push water in front of it. So we're going to have a crest here and a trough here. Both the crest and the trough will propagate as waves in either direction, in both directions. So the difference now, though, is that this landslide can continue, often for many, many minutes or hours down the slope, whereas in the case of a fault, it's over within a few seconds. So what happens is that as this proceeds down slope, it will continue to radiate or push a wave. Once we initiate this wave, it will take off at that same speed, root GH. But as this proceeds down the slope, it will continue to push a wave ahead of it all the way, which is called the coupled wave. So two very different wave regimes associated with the two different styles of tsunami. This simply shows a tsunami as it approaches shallower and shallower water, and we can see that the wavelength decreases enormously. The speed will decrease as well as we get into shallow water and frictional effects take over. So just some very quick case studies, just to give you an idea of the magnitude. 1964, this is the Alaskan earthquake, Good Friday earthquake. It was a magnitude 9.2. That's a great earthquake, very large earthquake. It occurred in Alaska, obviously, but it radiated tsunamis, which struck several communities up and down the west coast of North America, killed a total of 121 people, and the tsunamis were 6 meters high. And in one incident in Crescent City, California, there were actually 3 waves. The first wave struck, no one was killed. They thought, oh, let's go down to the harbor to see what was going on. So they went back down to the harbor, and in total 11 people were killed as a result of that incident. So just as a warning, for a practical warning, tsunamis aren't a single wave. It's a train of waves. And often the first is not necessarily the largest. It usually is, but not necessarily. So this is just some of the damage in Alaska. This is actually in Seward, Alaska. You can see that the wave that was created there locally swept boats ashore and did a considerable amount of destruction. Interestingly, in Seward, the wave in the harbor, there was an underwater landslide that actually gave rise to the largest tsunami, and it inundated the lower part of the town. Wiped it out. It's been cleaned up nicely. So that if you go there now in your RV and you want to park overnight, you can park where the tsunami struck before. So just bear that in mind. They've converted the area into an RV park. So the Indian Ocean tsunami, it was a fault-generated tsunami, and it occurred on Boxing Day in 2004 and killed 230,000 people. Certainly one of the most devastating natural disasters in recorded history. You can read all this. I'm sure you know all about that incident. Just some of the destruction in Indonesia as a result of that. It inundated broad areas of the land. This shows a broad area of destruction and the clipping here of the wave as it swept through the islands in this zone here. And very often what can happen is boats can create a lot of the destruction from a tsunami. Boats that are lifted out of the water and thrown onto infrastructure, houses, buildings, and so forth on shore. I did a study several years ago for Peter Phibbs' former company where they wanted to put a shore station in Japan, and they were planning to put it at about a few meters above sea level, immediately behind a fishing boat harbor. And so I pointed out to them that if there was a tsunami, all those fish boats would be sitting on top of their cable stations. So, and then just some more of the inshore destruction. A lot of it, as I say, caused by debris being swept by the tsunami, and just some of the inundation from that. Now back to Canadian tsunamis, and one that was actually created by an underwater landslide. This is the most devastating tsunami in Canadian recorded history. I'll come back to that distinction in a minute. It occurred, well, Canadian, it was actually British at the time, I suppose. Occurred in 1929 off the south coast of Newfoundland. It was a major earthquake, but remember that magic number of 7.5. This was a magnitude 7.2, and it occurred underneath the continental slope off the Grand Banks. It was felt through much of eastern Canada at that time. And most of the destruction was caused on the Burin Peninsula off southern Newfoundland, where 28 people, it's argued whether it was 27 or 28, but approximately 27 or 28 people were killed in that tsunami. So that's where it occurred. I won't go through this, as some of a repeat, but it occurred approximately in here. And what it did was, it triggered an underwater landslide. So it was actually the landslide itself that generated the tsunami, not the fault movement associated with the magnitude 7.2 earthquake. And it was felt far away, the Azores and over here in Portugal as well. I'll show you some tide gauge records. So this is what the tsunami looked like on a tide gauge in Halifax. Here on the upper left, you can see the tidal rhythm in here. And if we strip out the tide and make this a flat line and just see what the tsunami looked like, this is what it looked like. So it lasted many hours, oscillating back and forth during that period of time. When you go even as far away as Portugal, this is what the tsunami looked like. Still very detectable. And remember, these are very early records. This is very early instrumentation to record these. So this is the extent, as far as we knew it at the time that we did this work, of the failure mass off Newfoundland would be up here someplace. These are the Grand Banks here. This is called the Laurentian Trough, and just bear that in mind, that there's a trough across the continental shelf here. So this is the massive material that was let loose in that failure, or in that earthquake that gave rise to the tsunami. So I and some Russian colleagues tried to do some modeling of what this would look like using the best information we could from people at the Geological Survey of Canada Atlantic in terms of the volumes and the thicknesses of the materials and how they may fail and where they may flow. So here we can see the observed travel time from the source of the tsunami to hit shore. This is the Burin Peninsula here. And what our computations were. Some are pretty good, some are not so good. Some relate to how well we know the seafloor bathymetry. You remember the speed slows down as it gets into shallower water and so forth. So that's generally what it looked like. And this is simply the radiation pattern of the tsunami travel times. So this is a little animation. Now that's meant to describe, that little patch there is meant to describe the source of the landslide material. Now remember, there's a trough here. It's a deeper trough. So I'm going to start and stop this animation. Oops, I'm going to try to start and stop it. Sorry about that. There we go. So here we see the tsunami spreading away from the source. And I'm going to stop it about there. Remember that trough, which is deeper. Now remember, tsunami waves travel faster in deeper water. So what we see is that the tsunami is going to race up the Laurentian Trough here towards Anacostia Island. And obviously it's going to go very fast in the very deep water down here to the south. You can see these little funny ripples that are kind of circular in this area right here. That's caused by the occurrence of underwater seamounts. These are volcanic peaks that rise from the seafloor, and because this wave occupies the entire water column from the seafloor to the surface, that wave is striking those seamounts and refracting around them. Okay, so, whoop, sorry about that. Come on. Whoops. Oh, there we go. Okay. Just going to let it go a little bit farther here. So we can see the waves spreading down the coast of North America. You can see that interference right there where the hand is on the seamounts. So that right there is Bermuda. So the wave actually went round and round and round Bermuda for hours and hours. Unfortunately, there are no tide gauge records from Bermuda that would allow us to look at that. So that was definitely a landslide-generated tsunami. The earthquake simply was not capable of having produced the tsunami on its own. In July 1998, the most devastating tsunami of the 20th century occurred off Papua New Guinea. Killed about 2,200 people. And again, it was a magnitude 7.1 earthquake offshore, and it gave rise to a 12-meter high tsunami, which inundated the coastal area, and I'll show you in a minute, and killed everyone essentially instantly. And there were 2 villages that were completely destroyed. This shows where it was. This is Papua New Guinea. The failure was off in this area, and it created an underwater landslide. And this shows you the coastal area and gives you an idea of how high the tsunami was. There were villages on this bar or spit across the lagoon here, and they were struck, in this case, by tsunamis up to 12 to 15 meters high in this area. And again, it's very close to shore, so there would not have been very much time difference between that failure and the actual tsunami striking those villages. So what about our case here? Well, there's our coastline here, our route. So we would anticipate that if we had a fault and a landslide, it might be in this area. Okay, do we see any landslides out there? Sure. We see large areas that are probably landslide related. Up here we can see a landslide. Landslides in here in several. That's quite a good size one there. So these are small. They're probably not going to generate huge tsunamis, but nonetheless we do have a definite possibility of having very large underwater landslides on the continental margin where Neptune will be installed. So now what I'd like to do, if I'm not running too much over time, okay, is look a little bit away from the sorts of events that might occur on this coast in the open ocean, and look at a couple of, or 3, I think it is, coastal failures, both subaqueous and subaerial, that can give rise to tsunamis on a local level, and in the scheme of things could very well be the more destructive on this coast in the shorter time frame. The one that's quite well known here happened in 1975 near Kitimat, and there was an underwater landslide. About 27 million cubic meters of sediment slid into the fjord. It created a debris flow, which I'll show you in a minute, a big underwater mudslide, if you like, that continued down a very low gradient very low gradient slope on the floor of the fjord. Continued about 5 kilometers. And as it did so, it eroded the seafloor, added more material to it, and it created a tsunami that was estimated at from 8 to 11 meters high. It was very fortunate that it occurred at extreme low tide. In fact, that was one of the causative or conditioning factors, was that it did occur at an extreme low tide. There were no deaths. It happened on a Sunday morning, and there were very few people working in the area. There were a couple of people working right at the site of the failure, at the source of it. So that's where it occurred. There you can see Kitimat and the location of the Alcan facility there. And the Kitimat village over here was inundated, and had that been at high tide, there would have been many houses destroyed. This is just from the Vancouver Sun on the day. It's 3-4 meters. I have to go back and look. Yeah. So the freak wave roared up Douglas Channel, demolishing docks and swamping boats. They claimed it was 25 feet at the time, and so you can read the rest for yourself. And it did actually eat back onto the shoreline, so it increased the water depth close to shore. Just some statistics on the failure down below there. So when you map the landslide mass, this is what it looks like underwater. So here we can see this is the landslide mass, 5 kilometers long. Remember, the volume here is about 55 million cubic meters of mud. Something that I won't talk about, but these are actually little blocks of mud, they're about 50 meters across and up to 10 meters thick, that went sliding across the seafloor in front of this failure. So this is the mass that caused the tsunami, and what I'll do now is, this was some work of a graduate student of mine a couple of years ago, Andrei Skvortsov, who tried to model that underwater landslide, which has very peculiar properties in this particular case, this kind of mud flow, and tried to estimate what the wave height should have been and what the wave field would look like associated with that event. So here we can see 20 seconds after the failure. Remember, the failure occurred over here. Sorry, this is the source of the failure. This is the Kitimat village, the First Nations village, Haisla village over here. So here we can see, remember that first cartoon, we have a drawdown of water where the sediment is falling, and where it's pushing the water up, we have a crest. Now that crest is going to propagate away, and the trough will propagate away as well. So after 70 seconds, we see that at the Haisla village, we have a crest here that Andre calculated was about 11 meters. The previous estimates of 8 meters came from markings on pilings, so that those pilings may not have been at the site of the highest wave. But to the best of our modeling, we see, or Andre determined that it was about 11 meters high. Remember the coupled wave I talked about? This is the wave that's being pushed by the underwater landslide. There it is. And you can see it's proceeding down the fjord ahead of the underwater landslide as it moves down the axis of the fjord. And that's simply what the water oscillations look like through time. So if we look here at seconds, we can see that after about 70 seconds, the village, First Nations village, is hit by the first crest. Then that's followed by a trough and so forth. So this is simply the water level estimates from that event. Okay, what's this? Obviously, it's the CN Tower, so why am I showing you the CN Tower? Well, anybody know how big the CN Tower is? It's 534 meters high. Lop off the antennas, 525 meters. That's the height of the highest wave ever recorded on Earth. Okay? And it happened in Lituya Bay, Alaska, in 1958. There was a fault, a fair weather fault, that ruptured and gave rise to a good-sized earthquake. This is a magnitude 8 earthquake. But it wasn't the earthquake that caused the tsunami in this area. It was the failure of the side of the mountain that slid into the harbor and created a wave that was 524 meters high. It removed soil, and I'll show you some pictures in a minute. It destroyed 3 fish boats and killed 2 people, and swept fish boats up into the trees and over the bar. So this is where it occurred. This is the inlet. The mountain that failed is back up in here, right adjacent to that glacier that's you can see there. And the source of the landslide is over here. And as I say, that's the glacier we were just looking at. And all this white area here was inundated and the forest stripped away by the wave. And there you can see where we've totally stripped off this surface. Sorry about the black and white, but we've totally stripped off the forest in this area. Here you can see the inundated zone in this aerial photograph. And here you can see the new growth of trees in the foreground here. And here we can see that trim line where the wave hit. The source of the landslide's back in here. Okay, one last example. I've gone far too long. This is a night inlet, which you can see is this L-shaped fjord here. And we read in a popular book, which you can probably pick up in the BC Ferries in your next crossing, by Billy Proctor, who's an old-timer who lives on the coast here. And he just tells stories that he'd heard during his whole life. He's about 85 years old now. And this was one. So Quilati was the site of a big village, and the story I was told was a big part of the mountain across the inlet fell into the sea, which created a tidal wave that rolled across the inlet and drowned most of the village. Well, we started to dig into that because we thought, oh, this might be an interesting study. So with no knowledge, this is not a reserve land, so it had obviously not been occupied at the time that reserves were created, and it was a major commission at the beginning of the 20th century. So it was overlooked, probably because it hadn't been occupied. And so we went there and tried to see if we could find evidence of it. And it wouldn't take very long when we started to look at air photos to see that, wow, yes, there had been a very, very large landslide there. So this is the landslide source here. It's 840 meters high. The water depth here is approximately 500 meters deep. So we've got 1,300 meters of vertical relief here for this rock mass to fall into. I'll come back to when it happened. We estimated, as I'll show you in a minute, how we tried to estimate that. We know it happened sometime between 1520 and 1570. And we did multi-beam surveying in that area, and this is the mass of material here. This cone-shaped debris at the base of the slope here is the mass of material that we believe came in probably a single event from that slope. So we had some ROV work. We used rope posts, and we looked at this to try to estimate the porosity. In other words, how much is rock and how much is water, to estimate the original volume of that material. And from that, we tried to undertake some modeling. Rick Thompson, associated with Neptune, did the actual modeling of the wave. This is the village site that was reputedly inundated and everyone killed. It runs from about here to here. It's about 10 meters in width, and it's only a few meters above sea level. But it's in a beautiful funnel-shaped bay right opposite where the failure occurred, so there would only be an amplification of that wave as it traversed the inlet. Sorry, I should go back. Sorry. So basically, we estimate that the population was at least 100 and possibly close to 200 people living there at the time. Census data for that period is very, very difficult to determine. We only know the census starting in 1835, and by that point disease had ravaged many of the First Nations on this coast, so it's highly likely that the village was much larger. We do know that there were 4 chiefs that are commemorated on a pictograph nearby, who were killed in this event. So just based on something that the anthropologists know about how many people each chief would have in a numum, which is a grouping of native people, we would estimate that it's certainly between 100 and 200 people that were killed essentially instantaneously by that wave. They would have had no warning. The wave was 10 meters or more in height, probably more by the time with the run-up involved in it. Anyway, so I'll end it there. I just wanted to give you a glimpse at some tsunamis, some more relevant to Neptune than others.